the language of the universe.
But I don't understand it.
Welcome back, everybody. Not an episode, but it's a live. We're doing a live right now. We have the Instagram live going right here. We've got some questions coming in the chat. We're also going to answer questions on the Instagram post that we made.
Well, what is this? We haven't actually spoken about this. This is the 100K Q&A, by the way, to all of you viewers out there on YouTube. Quick thing. We tried to make it work on YouTube as a live stream, but unfortunately, I don't even know what went wrong. Like, we're still trying to figure it out. This was our very first stream, you know? So, unfortunately, the stream didn't go as planned, but we are on Instagram, as Parker just said. So, you know, obviously, the viewers on here are probably going to miss it, but... So, we've been on Instagram, and we have a few questions that we're going to be answering. So,
yes.
The 100K Q&A, let's get into it.
Okay, and also for the people that are in the live, you can, I think we're going to answer the Instagram questions first, make them, quick bullet round, and then you guys can ask questions in the chat, and we'll answer those questions.
By the way, Parker.
Boom.
Parker, I just want to mention one thing. Do you mind taking, a screenshot of all the pictures on Instagram and, posting it on sending it to me? Because I can't access it on my iPad, right? Yeah, we just started our live. So also the video for the YouTube watchers is not going to be very organized because, again, we're doing it simultaneously live and trying to record it for a later date. So it's a little interesting how we're going to do this. We're still trying to figure it out.
We've been at this for, an hour now? Trying to,
we've
literally
been
an
at this
hour
for quite some time. Parker
out.
and I were trying to figure it out, starting at 11:20, 11:30, and we couldn't figure it out since then. So yeah, we are back at it again. What's up, Johnny? Okay, thank you, Parker. Thank you. Okay, we got the questions.
Okay.
Let's get it going
do
question number 1.
So wait, the first, the top part is the second picture I sent you.
Oh.
So Terry actually has, wait, what? Oh my gosh, what is that? You have a caterpillar under your nose. Ray, that's you.
Oh. Yo.
I was hold up, but there's a caterpillar.
I was thinking something else.
All right.
Yo, Johnny, I'm becoming a man now. You know?
Yeah, right, I was playing chess on live. Anyways, okay, first question actually comes from Terry, who's in the chat right now. So, do you think there's a better definition for gravity? So, there actually is a better definition for gravity, and that comes through. It shines through in the theory of general relativity, which we haven't made a podcast on, and we probably won't for a very long time because, we're not at that level yet. But essentially...
So general relativity is mainly covered in graduate school. It's actually touched on, I believe, in 3rd and 4th year.
Yep.
But it's mainly covered, the bulk of it, in graduate studies, like in your master's or PhD program. Because, well, it is... think about it this way. Albert Einstein took 10 years to figure it out. Now, obviously, we're not figuring it out. But... obviously, that does have some level of complexity to it, right? So to totally understand the math behind it, it does require a sophisticated level of knowledge.
Yeah, at U of T, there's actually, I think they're both 4th year courses or they're both 3rd year courses, but there's you can take Relativity 1 and Relativity 2, which is pretty much just general relativity. And it's pretty cool because when you learn about special relativity, you assume an inertial frame or 2 inertial frames of reference that are moving relative to each other at a constant velocity, and then from there you derive all of the equations and all that stuff. But I actually watched a YouTube video. There's a Stanford lecture on general relativity, and it's actually really cool because the first thing you do is you don't assume inertial frames. You're just there are 2 frames moving with respect to each other. They're accelerating, they're doing all these things, and then from there you start deriving the equations. And so you can start deriving equations where there's a person in an elevator, the elevator is accelerating, and the planet is I don't know, moving in some way, and then everything.
Well, yeah,
is a lot more complicated.
The essence of it again is basically generalizing special relativity, hence the name general relativity,
Yes.
right? Like it's directly trying to just take that, because special relativity was built off of the notion that things are moving in reference in inertial frames. So now we're completely generalizing those inertial frames to just frames of references. So so we can have a lot more with general relativity. It opens
to answer
opens us up to a
the
lot.
question, basically the better definition for gravity is essentially just curvature of space-time, which is hard to imagine in your head because it's four-dimensional. But imagine instead of it being like 3 plus 1 dimension, like 3 space 1 time, imagine it's 2 plus 1 dimensions, and then the curvature is like the curving of the plane like down, and then like the marble like rotating around like that. But it's just the same thing but in 3 dimensions. So instead, like, I can't show it with my hands, but it's like curving like this, and then the things orbit around planets and stuff like that. Okay, I think that's good.
Yeah,
Next
moving
question.
on. What is your goal for this podcast, and where are you trying to go with it? Well, I don't think initially when we started this, we didn't really have a goal. I think our goal was just, hey, we love talking about math and physics. I mean, for those of you that probably don't know our history, Parker and I met in a residence, like a college residence in University of Toronto first year. And, like some nights we were just staying up, just talking some cool science stuff, So sometimes, it just felt like, well, why don't we just do that with a mic and post it online?
Yep.
So we didn't really have a goal in the beginning. But I think now we're starting to look in the horizon, and we have a few long-term goals, right? Like, I think...
yeah, I mean, we just play it by ear,
true.
I guess. Like, whatever happens, happens.
True.
But
we are going for that
bigger
100,000 followers, though. We are trying to... The 100,000
sure. I mean,
Spotify followers will be the day where...
We're definitely on the way there. Like, we're almost at 10,000 now. And then 10,000, like, you just keep making content, and then you just keep getting followers. I think that's how it goes. Okay, bye, Terry. Have a good
okay.
Have a good night.
See ya.
So yeah, I mean, I guess those are our long-term goals.
Yep, those are.
Next question. Is the universe a hologram?
Is the...
I don't think I can answer that question.
Check out our episode on is the universe a simulation, or is something like that, right? Yeah,
that was actually a nice episode.
Such a cool episode. I love that episode because we talk about exact questions like that. Is that possible? What is the extent of that possibility, and stuff like that. So we have another one that's kind of similar. I'm just looking at some similar questions, and I'm trying to like bunch them together. We already have like, why did you start this podcast? So we kind of, what was the motivation behind it? Again, it was just, Parker and me just talking, and we just wanted to post it. And what is the podcast, and like, what is your setup and stuff like that? I think we've already shared that. We have some cool mics here that we always have. We have our whole, again, on IG Live, we can obviously show it to you guys, but we won't be able to show it to you on the YouTube.
Yeah.
Maybe a quick turnaround for our
my audio is being recorded right here. We have the Zoom right here. This is what I look at. I look at Ray. And then here I got like my iPad with like information and keyboard, mouse, mic.
Yep.
There you go.
And this is my second screen. This is actually, so usually when I record, this is not on. This is only because I was streaming, so I thought I would keep it on. Because usually this light is here, glaring into my face, because I don't have the best lighting in the room. And boom, you see it. You see the camera. You see the laptop. Boom. You see the main setup. And then obviously me right here sitting on my beautiful chair, just relaxing.
All right.
That's our setup. Yep.
So next up, ever think about going live on Twitch? Well, kind of. We still got to figure that stuff out.
We can.
But I think... Because I know people like stream live on Twitch and YouTube at the same time.
Yo, I don't know, man. They obviously have some insane computers for that.
Yeah.
Like, I can't. Either I'm just using the wrong software, or my computer is not strong enough. I don't know, because it's just a really weird situation with the whole stream thing. I think we're gonna try and learn it. Is that a question? No, sorry. So I'm still reading the live. Okay, moving on. We have, what is your favorite math topic covered so far at U of T? Math topic, not course. Topic.
Topic? Oh, Stokes' theorem.
Oh,
Stokes' theorem.
that's a good one.
Definitely.
That's a good one. That's a good
Definitely.
choice. That's a very
Definitely.
good choice. That's a really good choice. Stokes' theorem is phenomenal. You want to maybe give us
Actually,
slight
like
description?
divergence theorem and Stokes' theorem together. Like,
You want to maybe like give a
craziest thing, but
small
essentially-
description about it? Because like I don't know if people have any idea about
Here's
it.
a small description.
Okay, let's hear it.
So, let's say you have a shape, right? You have a shape in 3 dimensions, and you have a vector field. Like, we can just pretend it's like at every point in 3 dimensions, you have a vector that tells you the speed and the direction of the wind, for example. So you just have arrows everywhere telling you, and the wind could be going like anywhere. It could be like tornado or whatever. And then so the divergence theorem states that the amount of wind that is leaving the shape is equal to this analogy is just terrible. I was gonna
Yeah, it's a little hard.
It's so
a little
hard.
hard to.
It's hard to explain, but essentially it's like the divergence of a vector field, which is essentially like how the extent to which the vectors are like pointing out of the shape is equal to like just the integral over the boundary.
Okay, to be
Anyways,
honest, I probably shouldn't have asked you to describe
I can't
it.
really explain this.
So
now.
Stokes' theorem and divergence theorem are both pretty complicated things. Like they both are dealing primarily with multivariable calculus, and you are dealing with them obviously, you know, in high levels of complexity. It was our very last unit that we were studying.
What do you mean primarily?
Sorry?
You said we're primarily dealing with multivariable like this is
okay. It is
multivariable.
Yeah, you're right.
Like,
it is multivariable calculus, and also this was Stokes and divergence theorem were both the very last unit of our second year multivariable calculus course. So safe to say it was hard.
What do you mean, econ brother? What do you mean by 46 million angles? I don't know what that means. Technically, there's unlimited angles because you can like separate it into however many angles as you want, but yeah.
So my favorite math topic, to be honest, like I think I mentioned this before, optimization. I think it's just a really cool, you know, set of rules, set of tools that you can use to basically take in any mathematical expression or any scalar valued function. So basically, you know, it can have many inputs just as one output. So for functions that satisfy
Wait, are you talking about like Lagrange?
Yeah, exactly. I'm talking about Lagrangian optimization and stuff like that. Basically finding, you know, maximums and minimums of functions. I think it's just a really cool thing, especially when you have, you know, 5 and 10 variables, when you're trying to model some pretty complicated real life scenarios, and you can just use optimization on these complicated functions. So I just think it's pretty cool. We also have a question in the comments from Purvi, from on Instagram, on our IG live. Sorry, have you ever discussed string theory? I think I really want to talk about this comment because we really want to.
We have kind of, yeah.
I mean, we haven't really gotten into it.
No, we have kind of
don't
talked
really
about
know
it
enough about it.
Dr. Rastigu.
But that was mainly loop
with
quantum
Dr.
gravity.
Rastigu.
That wasn't really string theory, right? That was actually they're kind of two opposing.
Yeah, but he did
almost,
talk
you know?
about it a little bit.
Yeah, exactly. So we might talk about it. We definitely will with a, you know, like a particle physicist or a physicist that actually works in string theory. Believe me, I have emailed string theorists before. But and when we get one, we will talk string theory. That episode is going to be so cool, believe me. But until then, I don't think we have enough qualification to really dive deep into string theory because, you know, there's a lot of math and there's a lot of deep understanding that we would just be able to, you know, touch the surface on, not really get through. You know what I mean?
All right.
So, yeah.
Next question, basically, Schrodinger's cat question mark? Yes. Exclamation point. All right. That's I don't know how to answer that, but you know. Anyways.
Okay, that was
how do you answer
cat? I mean,
Schrodinger's
it's pretty
cat?
cool.
Like
it's pretty cool.
Schrodinger's cat? I mean, I can kind of explain it, I guess, but essentially there's a cat in a box with like an isotope of radioactive element, and essentially we don't know when that element is going to, what is it, not decompose, what is it, decay. Yeah, we don't know when it's going to decay. And so basically, if you don't have access to the box, or you can't make measurements inside the box, you have no clue whether the cat is alive or dead, which means that, quantum mechanically speaking, the cat is alive and dead at the same time. Its state is a superposition of two states at the same time. Mm-hmm. Until you make a measurement, that's when its state essentially collapses on one of the options.
Mm-hmm. And yeah, so the big thing about Schrodinger's cat is basically it deals with the big question of how do you interpret quantum mechanics? Because one way, the famous way, is the Copenhagen interpretation, which basically states when you make that observation, the wave function, or that thing that Parker was saying where it describes both that superposition of the state, it collapses into one of them. So either the cat is dead or the cat's alive the moment you make that observation, the moment you make that measurement. And that's the Copenhagen interpretation. Right. Now, there are other interpretations of quantum mechanics. And I think we've spoken about, the many worlds interpretation, for example, which I really love, which is when the moment you open the box, it creates a parallel universe where one of them, the cat, is alive and one of them is dead. So the wave function never collapses. So that's just another way of interpreting it. So I think that's the big thing of Schrodinger's cat, because it's really asking you, well, how do you look at quantum mechanics, right?
Yeah, so Purvi, by the way, we have an entire episode on black holes.
It's just called Black Holes. It's literally called Black Holes.
It's called Black Holes.
Yeah, it's actually pretty nice.
All right, next question. What do you think of the results in the recent Muon G-2 experiment? I think it's crazy, to say the least. I don't really have that kind of level of knowledge of particle physics to really comment on it and be like, oh, I think this and this. It opens up the doors to the future of physics, which is really interesting. And hopefully one day, if I decide to go into particle physics, which I don't know if I will, to be honest, but if I want to read up on it, maybe learn a bit about what they're actually doing at Fermilab, that would be something cool to learn about.
Yeah, so for the G-2 experiment, I think it could potentially be it could actually be a breakthrough, a start of a breakthrough. Basically, for those people that are not exactly aware of what this G-2 experiment might be, it's basically in Fermilab. It's this famous particle accelerator here in America, where they measured, or were trying to measure, the magnetic spin of a muon, basically. And that's called a G factor. So I believe, basically, the idea, again, I'm not going to say any of the numbers because I'm not even sure about them, but the essence of the experiment was that their calculations with the standard model of particle physics said the G factor should be this. When they actually measured it, it was a little more. How much more? It was 0.000. I believe it was 4 zeros and 1 or something, very, very tiny difference. But that tiny difference could potentially be the signs to the fact that our standard model is not complete. There's some missing elements, because if we were right, it would have been exactly what we had predicted, but it wasn't. So there's something else that we're missing. So the big thing about this experiment is that, we might have just discovered that we're not done with, I think we always knew that we're not done with science or particle physics, but this kind of proved it, that almost proved it, that the standard model is not complete. And there might just be some more particles that we can see. Mm-hmm. Physics has no future.
Brandon in the chat says physics has no future. The thing is that every time someone has said that in history, they were just proved very wrong. For example, at the end of the 19th century, people thought that Newton had figured out, Newton with Newtonian mechanics, and then Boltzmann and Maxwell with electromagnetism, they thought they had literally everything figured out. And physicists were literally thinking okay, we are done with physics. We have figured everything out. And then, of course, people started looking at atoms, and then they figured out that, wait, there is a lot of things that we do not know. And so, to say that physics has no future right now is like the exact same situation that humans have been in before. And so we are going to get proved wrong. For example, dark matter. We don't know what that is. We have no clue what that is. Are we going to figure it out one day? Probably, to be honest. But, it's going to take some ideas.
It could take like decades. It could take centuries, man. We have no idea really what the time frame is. But,
I think it's gonna happen sooner than later.
But I think that's the whole essence of science, right? The whole point of it is going after the truth, trying to figure out the truth. I was watching this episode, and I don't know how many of you guys watch Young Sheldon, but let me tell you why I bring this up. I was watching this one episode that just got to me, and it was so beautiful the way they describe it. Basically, young Sheldon, for any of you who watch Big Bang Theory, Sheldon, this genius. So when he was a kid, basically, he had this option. Again, this was all a dream. This was his dream. He had an option of knowing everything there is to know about science, and he wanted to take that option. And in his dream, there were all these scientists saying, well, what are you going to do with that? What's the point of that? The entire point of science is going after the truth. You don't want the truth handed to you. If you just knew everything, then what's the point of finding anything out, right? If all of the knowledge is available to you, then any more knowledge is not interesting because you already know everything. You know what I mean? So the entire point of science is simply to search, to continue to search, and to keep moving on. So I think, as you very well put it, it's just going to continue to be it always will be the future, because there's always more to discover. There's always more to know, and that's just never going to end.
So there's like old questions in the live really quick. Let's just answer them quickly. So we're both going into third year, and Ray is a physics stats major, and I am a astrophysics specialist. Next up, what are we considering for grad school? I don't know, to be honest, but I think like if I do go to grad school, it's probably just going to be in astrophysics. And what about you, Rehan?
Damn. To be honest, when I just came into university, when I came into undergrad, I was almost certain that I was going to, continue in masters, continue probably like PhD or something, into like physics, like a physics specialist. I was really intrigued with particle physics at that time. And I was just like, this is almost definitely going to happen. Then I spent 2 years in university, and oh my God, like when they tell you that university opens up your experiences and opens up your chances to see new things, they're totally right. Like I've taken these courses, these programs, these courses, like these, for example, I've taken, tutorials and stuff like that where you have like one-on-ones with TAs and, where you speak to, people in that program, and your entire viewpoint of some courses, your entire viewpoint of some subjects change. I was talking to like a statistics teaching assistant one time, and and he was talking about some crazy stuff that, I had never even thought about in different programs. So at this point, I actually don't have an answer for what I'm going to be doing in grad school. I mean, I am quite certain that by the end of fourth year, I will have that answer. But right now, I think there's just a lot of things that in second year, I took a lot of new courses that I hadn't done in first. And I'm just really excited with a lot of the opportunities that, U of T and the universities have to offer. So I'm definitely going to, continue looking at it, continue enjoying it. But I do not have an answer for that just yet. Yeah, Young Sheldon is fire. Okay. Yeah, that's cool.
Can we talk about space-time diagrams? Essentially, isn't it like broken down into like 2 dimensions? So basically you have like time on one axis, and then like the space is like a plane, and then it shows how like when it moves across, like you start at the Big Bang, I think, and it's just a singularity, and then as you move across, it creates like a cone because of how the universe expands. And it's kind of what's actually cool about like the discovery of the Big Bang is that you realize that like, yeah, this is kind of a hard topic to introduce right now, but I was like the older light is, the more redshifted it is, because as you travel through the universe for a really long time and the universe stretches, your wavelength stretches, and so your light becomes more red. And so if you look at these super old galaxies and quasars, for example, you'll see like this crazy red-shifted light, and it's hardly recognizable until you like account for that redshift. And then just by like absorbing light into a detector and then figuring out how much that light has been redshifted, you can actually tell the age of where that light came from. And so, for example, things like the cosmic microwave background radiation, it's actually just light that has been redshifted all the way into, it's not even microwaves anymore, right? Isn't it like past microwaves now?
It's much past, because it's going to be elongated for sure, right? Like past, it's all, you know, past infrared and stuff. It's, you know, you see it into those.
But yeah, that's all I wanted to say.
I don't know if that
that
was the question, though. I think they were mainly talking about like space-time diagrams. Not. I don't know if they were talking about like redshift, like, you know, cones, like light cones and stuff.
Yeah, but I mean, like that's what.
Well, like for example, like a space-time diagram is like on one axis you have like, you know, your CT, and one you have X. I don't know if anyone. I don't know if anyone recognizes.
No, I know what that
yeah,
is.
I mean, obviously you do. I'm saying if anyone recognizes
Oh,
those
sorry.
variables. So I'm saying like so one of them is basically measuring how time changes. But now here's the thing: the entire point of space-time diagrams is so that you can make calculations pertaining to special relativity. So when your speeds are close to the speed of light, those are called relativistic speeds. That is when you use space-time diagrams, basically drawing the path in a space-time coordinate instead of in a spatial coordinate.
I don't know if that's what the question was about, though.
Oh, was it not?
Talking about space-time, like
light cones and stuff, and this is all about it.
Yeah. Oh.
Like, this is just understanding like how to plot an object moving at relativistic speeds, because in this diagram you are able to, you know, calculate the length contraction and the time dilation via looking at the graph. Just via looking at the graph, you know, instead of actually, you know, doing the math and stuff depending on the object's motion. So there's a lot of advantages simply just to look at it. It's basically the Cartesian plane, but for those video watchers, this is not even on audio. So it's basically the Cartesian plane, but it's a little bit skewed, basically, again, with relativistic speeds, so that whoever's moving fast, the time is moving slow. I don't know if this really makes that much sense, but if you like look up a space-time diagram, you might see that shifted axis, and that's basically what I'm talking about. Yeah.
All right, let's blast through these questions here. So, how much of the universe do you believe we discovered? Yeah, 4% is not accurate, actually. If you listen to the Jill Tarter episode, she said that the amount of the universe that we've observed, not observed, I guess, you know, observed with like telescopes and things like that, is comparable to like a hot tub amount of water versus the ocean, you know, if the ocean was the universe. So a lot less than 4%. But it's growing because we have a lot of telescopes and things working around the clock to look at the sky to see like if there's things we've never seen before.
But also here's the thing, right? If we can figure out, I don't even know again where and how this is possible, but if we can't figure out dark matter, dark energy, or like we can think about things that constitute them, right? Right now, we think dark matter is one type of matter. And in that, was it a Jill Tarter? I don't remember which episode it was. No. It was not the Jill Tarter episode. It was the Miriam Diamond episode. It was the Dr. Diamond episode where we were talking about dark matter, how there could be a whole standard model of particle physics for dark matter.
Yeah.
There could literally be a whole new set of particles for the dark candidates, right? So if we're like, you know, we get any closer to dark matter or dark energy, I think that's when we can start to truly judge how much of the universe we know. But before we even know that, like, as of right now, like, we hardly know anything. Like, we're just assuming things, you know? Like, we see galaxies, we make observations, and we write down what we think makes sense based on our observations. But to be honest, like, 200, 300, 400 years from now, 500,000 years from now, if we see something else, if we observe something else, we might have to change that theory. So a lot of these theories are based off of observations, and, they might be able to be disputed in the far future. So, yeah, much less than 4%, basically. For sure.
Yeah. Do we watch Rick and Morty? I have, actually.
I
haven't seen season 4.
I love that show. But, yeah, season 5, who knows when there's going to be the next
5.
season. What? Yeah.
Wait, is it season 4? Yeah, season 5 I haven't seen. Just because, like, I think about it, and then, like, I forget about it, and then, just haven't seen it. Anyways. So,
what more questions? Oh, they're talking about cones. They're talking about cones.
What's Bourbaki? Bourbaki.
Unfortunate part about the universe. Yes, I would highly recommend everyone to watch Kurzgesagt's new video. I mean, or at least new when we release this. Wait, did I pronounce it wrong? Isn't it Kurzgesagt?
Yeah, it's Kurzgesagt.
Oh, Kurzgesagt. Sorry, Kurzgesagt. Sorry, I mispronounced that. Kurzgesagt's new video, The Limits of Humanity. What a beautiful video.
Very
Basically,
video.
Exactly tackling that question, Purvi, where you're asking, there will be a time where we won't be able to see anything, because as of right now, the universe is receding from us, right? The entire universe is expanding at a very fast rate. And interestingly enough, it's accelerating in its expansion, almost to the point, not almost, it is to the point where, it's faster than the speed of light. So if the universe is expanding faster than the speed of light, and obviously light is not faster than the speed of light, there are going to be a lot of galaxies, and going to be one fine day, billions and billions of years later, where the night sky will be nothing, just black. Because we won't be able to see anything, all the light would have left our universe, and everything would be so far apart that no light would be able to reach anywhere. So that's a possible future of humanity,
Yeah, for sure.
Oh, Westworld. Oh my God, what a beautiful show. I think I've mentioned this before on the podcast. It's such an amazing show. It really gets you thinking, man. It really gets you thinking about consciousness and stuff like that. I think we also talk about this in
grammar podcast.
In an episode. I forget which one, but it was such a cool concept, thinking about artificial consciousness and really asking the question if that is possible. I think it's really cool. Yeah. Any more
hold on,
any more questions we got? Let's see. I like the Twitch ID.
So Brandon says that the only physics that makes sense is classical mechanics.
Oh my.
Which is not true, actually, because the thing about physics is that you see something, like it's either theoretical or experimental. But, let's say we're talking about experimental physics, which a lot of quantum mechanics is experimental. I actually don't know the proportion, but anyways, let's say you're trying to figure out the structure of an atom, and so what you do is you shoot alpha particles at atoms, and you see that some of them like ricochet, some of them get like shot at different angles and things like that. And then you have to adjust your ideas based on what you see, because what you see is literally an event, something that happened in the physical universe. So it's not like something that's impossible because you're seeing it right in front of your eyes. So if your theories don't match up with what you see, you have to make a new theory. And so like the structure of the atom was essentially like at the beginning of the quantum revolution, because as soon as you start dealing with single atoms, you have to start dealing with like electrons, electron states, spin, and all that stuff to explain things that we see in the physical universe. And so like to say that the only thing that makes sense is classical mechanics is literally like the opposite, because you see things that happen and then you explain it like because it happened, so it makes like perfect sense because you're just explaining what you're seeing.
Also, quantum mechanics is a very nice interpretation of the universe, I believe, because classical mechanics is of a way where, what is classical mechanics? You know the properties of the object and you're trying to predict the future. That's always the idea with classical mechanics. You either know its speed and momentum, and you're trying to figure out something, usually X and P are the two things that in classical mechanics. It's one of the very base things that you know. When I say P, again,
position and momentum.
Again, when I say P, though, you don't always know momentum, but you do know velocity, which translates to momentum. That's the connection that I'm making. So you always know the position and the velocity of the particle, basically, or of the object that you're dealing with in classical mechanics. And again, the entire point of it is using different versions. You can use Newtonian mechanics, you can use Lagrangian mechanics, you can use Hamiltonian mechanics. So using different, classical mechanics strategies or techniques, you can predict the future of an object. But now comes quantum mechanics, where it says you can't know the position and the speed or the momentum of the particle at the same time, i.e., there's some level of uncertainty to both of them. And that is where this whole question of determining the future becomes a little interesting. Well, how do we do that when you don't have X and P? Because those are the two basic things you need. That's where quantum mechanics comes in, right? That's where
we're gonna be posting this on YouTube, by the way. Oh, sorry.
Oh, yeah. So that's where you can.
I was just answering a question. Mm-hmm. We're gonna be posting the live on YouTube. I don't know if we're gonna keep it on Instagram.
You want to keep it on? I mean, like, we can just keep. Do you guys want us to keep it on Instagram?
We actually could.
We can just maybe. Yeah. I mean, there's no harm to doing that, right? Okay, we have another question. I recommend.
Okay, so definitely. Wait. Would you say you've gotten more out of your physics knowledge that you talk about on these podcasts from your university physics classes or outside resources such as podcasts or published papers? 100% from university. Like, pretty much everything I know comes from university. And then, like, because what happens is that you build, like, a foundation from, like, the things you learn in university, and then from there you can understand different things. Like, for example, I took a class on quantum mechanics, and then I started reading about quantum mechanics. Obviously, I learned, like, extra concepts from reading books, but basically, like, it all traces back to what I learned in university. And so
now here's my take on it, right? Like, yes, obviously, I very much respect university for all the knowledge and everything it's given me, but I think a bigger point of university is to teach you how to learn. It's not really teaching you knowledge, because to be honest, like, completely frank, like, there's a lot of knowledge in my head from, like, random YouTube videos, TED Ed, for example. I love their YouTube channel. I love it. Some random spites of knowledge that just sits in my head from there, and it's just like, that's the knowledge that I actually use on a daily basis, So,
but Ray, the question was...
No, I know what the question was.
The knowledge that we talk about on the podcast.
I know it was physics knowledge, talking about podcast versus university. But here's the thing.
No. It's not physics knowledge that we use to talk about on the podcast.
Oh, like, sorry, I misunderstood the question. Okay, yeah, then it's obviously university. Okay, most of our podcast information is coming from our university because the foundations were built from there. But obviously, when we're, talking about more and more complex topics, again, I resort to my original point, the fact that university teaches you how to learn. It doesn't really, like, even though it does teach you stuff, it does educate you. It mainly teaches you how to learn. Because with that knowledge on how to do this, how to learn, you can learn anything. Because when you know the foundations of quantum mechanics, when you can understand those math, when you can understand Dirac notation, when you can understand, bras and kets, like, if anyone's taken quantum mechanics, you might know that lingo. So if you can just understand the foundation, you can open quantum mechanics papers and understand the idea behind them. Like, you can understand things that is not directly taught to you from school. So I think that's also a major advantage that school poses, just teaches you the ability to learn more and more, Yeah. Yeah.
So I think I'm going to have to cut it off here because I haven't eaten anything all day today. So
really? Hungry. I didn't even know that.
Yeah.
It's
I haven't had anything to eat.
This guy.
Yeah, I know. We're going to do another Q&A, of course.
100%.
250K Q&A.
Ooh, we might have to.
Crazy.
250K Q&A. And believe me, we will get the stream fixed. hopefully. The thing is, I don't even know what is wrong, right? So I'm just gonna ask like my friends who commonly stream. Like I have some friends with MacBooks and stuff that do this stuff, so I'm just gonna see what they say, see if my problem is common and stuff like that. Okay, we have one last question. Maybe we can take it because we're still on IG Live. We have, what classes did y'all take in high school? A lot of people maybe kind of curious because we're in high school too. Yeah, so what classes did we take in high school? I came into high school in grade 10. I came from India. I came to Canada in grade 10 and I started high school. And for my very first 6-7 months of high school, I was just really interested in physics. I was interested in science, but mainly in the physics because I wanted to understand why things work. And that the question of why was really, intriguing. And that's the common physicists or scientists saying. They like the question why. So in high school, again, I was mainly just taking physics courses, advanced math, AP physics, stuff like that, and mainly focusing on courses like that. What about you, Parker? Did you take mainly physics courses, or did you stick with some other stuff? Because I believe you also came into physics mainly in university, right?
I mean, in high school, I took physics and calculus and functions.
Mm-hmm. So all the necessary stuff for science.
Basically
all the necessary stuff for science. So your
know how
functions,
to write
advanced functions, your calculus, your physics. And again, my school offered the AP program, so I really took that. I really liked that. The video on human limitations is, I think, called The Limit of Humanity YouTube or something. Channel. Right?
Kurzgesagt.
Yeah, that's the name of the channel, Kurzgesagt.
Yeah, it's the most recent video.
Yep. It's really good. Okay, so yeah, Parker, you should definitely go eat. I think we can end it here. Thank you, everyone, for joining us on Instagram Live. It was really nice talking to you.
Thank you for all of the
those
questions.
People that watch the YouTube video. Yeah, maybe these guys are gonna be like, maybe I'll join next time. Maybe.
All right. Well, this has been Q&A, the very first official live Q&A that we do on Instagram.
Yep.
So yeah, I guess we're just gonna end it here. Peace out, everybody.
See you guys. See ya.